Another important properties of integral is switch interval. To learn about it, let's look into this problem. The graph of f is shown below. Let's gx equal to integral from 0 to x ft dt. So it's probably look unfamiliar because when we learn about the fundamental principle of integral, it's always start from c to from x to c or something. But no problem, it's just as simple. In this case, we just substitute anything with x using minus 2. So in this case, g of 2 equal to integral from 0 to minus 2 f t dt. Okay, and look here, this is not fx dx or area under the curve because of, you see here the interval is from bigger to the lower, so we need to be able to apply the rule of integration as we have learned earlier. So we need to rewrite this one. So this one then equal to, because we switch the interval, so there will be a negative of minus 2 to 0 ft dt, and here you can see it is area under the curve from minus 2 to 0, so it's area under the curve from minus 2 to 0, so it's this area, so it is 1 2 3 4 5, this is half and this is half, so this one is 6, so this one equal to 6. Next, how to find the derivative when x is on the lower bound. So when x in the lower bound, this is not what we see in the fundamental of the fundamental theorem of integral. So we can use the properties we have learned before by rewriting this into form. For example, here we want to switch the interval, so it's a d of dx of minus from instead of x to 3, now we use it from 3 to x square root of absolute cos t dt, and this one is then equal to minus d over dx of integral from 3 to x square root of cos t dt, and we can solve this by using the fundamental theorem of calculus, and this one actually equal to minus square root of cos x absolute. The final properties of integral that we will learn is finding derivative using the fundamental theorem of calculus, where we have a function where x is in both bounds. As you can see here, you have an fx equal to integral cos of t over t dt from x to x squared. We are asked to find the f prime of x, or f accent of x, or a derivation of the fx. So the easiest way to understand this problem is by looking back into the concept of integral, which is the area under the curve. Let's say we have area under the curve. This is a y, this is an x, and you will have an fx. So I can simplify, I can visualize the problem given on the left by visualizing it as an area under the curve of fx from let's say here x to x squared on the right. Yeah, x squared. It can be from x squared to x depending on the condition. So to be able to break the bounds, to insert a constant, I'm going to put some constant in the middle, where let's say this is a c, in which here the constant c is larger than x and less than x squared. In this case, I can define the area between x to x squared as the integral from x to c f(x) dx plus integral from c to x squared f(x) dx. Okay, so I can use this definition to solve the problem given earlier. So in this case, then f prime of x then equal to integral from x to c cos of t over t dt plus integral from c to x squared cos t over t dt. And if you look here, the first term we need to reverse it, so it's from a constant to x, so that we can apply the fundamental theorem of calculus to solve this derivation. So then I'll put it as minus cx, because we exchange the interval, integral from minus integral from c to x cosine of t over t dt plus integral from c to x squared cosine of t over t dt. Okay, the first term I can easily solve using the fundamental theorem of calculus. That will be equal to minus cosine of x dx, cosine of x over x, and the one on the right, the same thing, we can use chain rule to solve this problem, and this will be then cosines of x squared over x squared times the derivation of the x squared, which is 2x. Okay, so then we can cancel this guy and this guy, so then we will have minus cosine of x over x plus 2 times cosine of x squared over x, or we can simplify this into 2 cosine of x squared minus cosine of x over x.